All right, welcome everyone. We are on week 5 of our Waterloo robot learning group. I see a lot of new faces today, so I'm just going to maybe give you a quick recap of what we do. So the goal is to sort of understand what is the frontier of robot learning. Robot learning in general is just a field where it's like, how do we apply learning-based methods to robotics? And so a lot of what we focus on is manipulation and sort of like pick and place, or more complex like folding a t-shirt. But it could also apply to locomotion, like if you have a humanoid and teaching it to walk, things like that. But today, the topic we're going to be covering is data collection. And there's going to be a paper, Dexumi, that we'll quickly cover. And the reason we picked this topic is because if you think about what currently is the state of the art, a lot of the robot foundation models, they take a lot of data in. And this data needs to be collected somehow. They're usually collected by humans. It could be sometimes procedurally generated with code. But most of the time, there's humans in the loop who are collecting this data. And so if you think about, if there's humans collecting data, and you're gonna need a lot of data to collect, and some methods are better than the other, and there are different trade-offs. So I think it's a worthwhile discussion to be had today. And before we dive in, is there any questions on just anything in general, maybe the reading group or the topic for today? And can I just get a sense of, is everyone from, like, who here is from autonomous? Like, who here works on maybe robot arms? Who here works on, okay, who here works on robot arms, for example? And who here works on self-driving cars? And then who here does something else, or like doesn't know much about robotics? Okay, cool. Okay, that's good to know. So first of all, I want to thank our sponsors. So we have 2 sponsors, Palatio and BracketBot. So please check them out. They were the reason you have free pizza today. So thank you guys. So let's talk about data collection. And I'm going to try to make this very interactive. So first of all, as I briefly mentioned, right, like why do we need data collection? It's because the current paradigm that we're under is imitation learning. So what imitation learning basically is you have some expert demonstrations. So maybe like if you're teaching a robot how to fold a t-shirt, what you're going to do is you're going to collect a very big data set of how you would fold a t-shirt. And then you're going to train some model, right? For example, Pi 0.5, or it could be like OpenVLA, any of these robot foundation models. And it's going to learn to sort of imitate what you did. And the difference between doing imitation learning and just like, because you could just replay the data set, right? But what you want the policy to do is sort of like be conditioned on things like images, right? So you could just, if you record a demonstration and you replay it back, that's sort of like just blindly replaying whatever you did, right? But you actually want it to fold a t-shirt. If the t-shirt is here or here, you want your policy or your model to act differently based on where the t-shirt is. So that's how we train a model through this imitation learning paradigm. And actually, it's very similar to, if you think about LLMs, what we're doing is very similar, right? Except that instead of working with a robotics data set, it's just text, right? So what we're doing in LLM world is we have a bunch of tokens, and we have sort of like this corpus of text, and we want our policy to maximize the probability of the particular token that is actually in the original text, right? So you have a bunch of tokens, and you want to maximize this particular token. And in this case, instead of tokens, we're looking at actions. We want to maximize the probability of a particular action given a state. But the issue in robotics is, as I said, is very hard to get robotics data, right? So for LLMs, you just have like a bunch of really high quality data like Wikipedia, you have books. It's very easy to get this data, right? But for robotics, it's not so clear. We're very data poor. And so it's why, recently, if you look at a lot of the robot learning startups, what they're doing is they're trying to figure out how to get this data in-house. So there's a lot of like teleoperating systems. And here I put a side note that maybe you can get away without data collection. So for example, for self-driving, there's parts of it where you, for example, label bounding boxes, but other parts of the stack, like the planning and the controls, you don't necessarily need to have expert demonstrations. They don't really do imitation learning. And also another way you could do it is doing RL from scratch, so reinforcement learning. And in this case, for example, if you look at AlphaZero, you sort of just have a policy that learns from scratch on its own, right? And it will just learn from experience, learn what is good, what is bad, and it's going to just purely learn from its own interactions within the environment. The reason it doesn't really work right now in manipulation is that if you train a manipulator from scratch, it's the sort of like dimension is so big of like what possible actions you can do that it just ends up being like it takes infinite time to actually complete a task successfully. So that's like if you work with very sparse rewards. So generally what people do is they'll train some sort of policy from imitation learning and then improve it through RL. Working in RL from scratch, at least for manipulation, is really, really hard, and it doesn't really work. So yeah, that's sort of why we need to collect data. And I put here like scaling laws because this is just something to think about. It's like how much data do we actually need to have very strong robot or policies that can generalize and can do all the things that LLMs can do, but in the context of robotics. Is there any questions on what I've covered so far? Yeah.
So AlphaZero or like DeepMind's model with RL, did they still use SIM?
Did they still use? Well, it's.
Because isn't that a form of data collection then, like having different assets?
So what they do in AlphaZero, from my high-level understanding, is they have in AlphaZero they play Go, right? And what they'll do is they have a model of how Go works, and then they'll play the model or the policy will play games to Go, right? And it'll play against itself, and then it'll reach an end state where it's like one or the other wins or loses, and then from that terminal state, you sort of learn, okay, the things I did, for the winner, it's like, oh, this is good. And for the loser, it's like, the things I did was bad. So you do all these rollouts, and then you can learn a value function for how good a particular state is. So does that answer your question? Okay. Any other questions? Okay. So yeah, let's talk about what people did to get this data. So there was like the Space Mouse, and so with the Space Mouse, what you do is, you can kind of clearly see, you can imagine the robot, the way you control it is, so let's say the robot has 6 motors. What you can do is you figure out what is this end effector pose, and then you sort of control it to the end effector pose. So you need to do inverse kinematics, and you sort of control it through inverse kinematics. And then kinesthetic teaching is something I learned about recently, which is very interesting. And they did a lot of this before. And the idea is, if you have very compliant robots, what you can do is sort of show it. If you want to teach you how to do pick and place, you should like push the motors around and sort of like what he's doing, taking the gripper and showing it how to do this pick and place. And then there's also what I talked about, procedurally generating. So for example, in simulation, it's very easy to know where your objects are. And so what you can do is like maybe hard code some path. Like, okay, I know the object is here, I want it there. I know sort of like how the robot arm needs to move to pick and place it. Procedural generation can become harder once you work with like soft bodies, or sometimes like it's really hard to procedurally generate paths. But at least for simple pick and place, it's a way of doing it. And then really, currently, what's being done is sort of this teleoperation paradigm. So these are like very, very common, what people are using if you look at a lot of these robot learning startups. So there's Aloha, Jello, and VR teleoperation. But they're all sort of like similar ideas where you as a human, what you're going to do is you have some sort of leader set up. And then let's say you're trying to collect a data set for how to pick up an object. Instead of you yourself picking up the object, you have like a robot next to you or in front of you, and you're going to control it through this setup, and then you're going to watch the robot pick up the object, and essentially you sort of collect it, you control it through this teleoperation setup. So you can do this with like another physical copy of the robot, but in a smaller form factor, or you can use a VR headset. Very similar idea. In the VR headset, what you do is like track where your hands are. The VR teleoperation setup is a bit harder to get right, because generally in this kind of setup, this sort of is like a one-to-one mapping of this robot, but in a smaller form factor. Whereas this one, for example, generally, like if it's a parallel gripper and you have 5 fingers, right, and you want to control like how the gripper opens and closes, you might need to do some remapping. Maybe you ignore these 3 fingers and only track the index and the thumb. So these are considerations that you need to think about when you do VR teleoperation. Any questions about this so far? Okay. For robot hands, it's very similar, right? So these teleoperation setups that I've shown are only for parallel grippers, where it's like a gripper like this. But if you're working with hands, you can use gloves, or you can also do VR teleop. But then you track all 5 fingers. Again, in the VR setup, there's sort of like this embodiment gap, because maybe your robot hand only has 3 or 4 fingers, but you as a human have 5 fingers, and also the length of your fingers are different from maybe what the length of the robot arm fingers are. And so there's this gap that could be an issue downstream when you train your policy. And here I have a personal anecdote to show sort of like some of the limitations with teleoperation, because so let's just play the video.
Sometimes there won't be a solution.
So this is actually a robot arm that I'm currently working on as part of our capstone. And we have Mulek, who's in the audience, who is trying to use the teleoperation setup to fold the t-shirt. And you can see that it's definitely not as intuitive, right? So if you yourself, you're folding t-shirts, like you can just do it in like 2 seconds. But because you're teleoperating, you're sort of like visualizing yourself to this robot. And there's sort of like there's latency, and there's sort of like, you're not used to just using these parallel grippers, you're used to just using all 5 of your fingers. You see that we end up just being a lot slower at folding the t-shirt. So you can imagine like a more professional or like a better teleoperator will get used to this setup and can like close this gap and can collect data at a faster speed. But at the end of the day, you're never going to get sort of like the human level performance, at least for these like highly dexterous tasks, like folding a t-shirt. Here's my computer crashed, I think, or something. Yeah, and then we have, I think we have Archie here, who's also in the audience, who's trying to fold the t-shirt. And then Greg was the best, I think, at doing this. So yeah, so if we don't rely on teleoperation, what is our alternative, right? So we saw like kinesthetic teaching, right? So that's like a bit closer to maybe something that we feel like as humans is more intuitive. And there's also, so these are some of the techniques. So there's UMI. These are sort of grippers that you're not directly using your hands, but you're taking these grippers and you're sort of like, you're using them more directly. So you're not sort of like looking at a robot arm and then you're sort of like controlling it. The data set is just you and these grippers. And what they'll do is afterwards, when you want it to work on a robot, you'll have like a very similar version of these grippers slapped onto a robot. And then that's sort of how you deal with this problem. So what the policy sees is just what these cameras sees. And yeah, what these cameras see. So you don't, this part of the arm is not a part of the data set. But you can imagine like if I had a third person camera and looking downwards, and it sees my arm when I'm collecting the data, there's going to be some visual gap, right? And there's dex cap and ego dex. So I think EgoDex is really just the most intuitive and ideally what we want, right? This is like the fastest way to get data is you slap a GoPro on yourself or some sort of first-person view camera, and you just start collecting data, right? Because then you use your hands and you collect the data. But there are many limitations of this, or like many problems that we still haven't fully figured out. Number one, for example, is like, let's say you pick up an object, right? Let's say I pick up my phone. When I'm like this, my fingers are sort of occluded, right? If I use my first-person view camera, and so sometimes you just don't fully know the state of your fingers. It's fully occluded. Whereas if you have a teleoperation system, you always know what the state of your robot is. So DexCap was good for this. They put like cameras from the perspective of their fingers, so that if it's like this, the camera can still see the fingers, and you sort of know the position of your fingers at all times. Do you want to show your thing?
I mean, I'll just pass it around. It's not assembled right now, but this is a grouper that is generally used for teleoperation.
Yeah, so this is like similar to the UMI setup, right? So you would use this, and instead of a GoPro, you have just your iPhone.
So you have your iPhone right here, and it's usually a string-based system, and so you can start recording while going on the flight here.
Yeah.
That's not the idea. It's unassembled, so I don't care.
Yeah. Very cool. And as I was putting up this slide, we have all these teleoperation and non-teleoperation setups, and sort of like, what are the trade-offs? I sort of put it down like in this diagram. Did Andy break it?
That's fine. It's already just pass it around as it is.
Yeah, try not to destroy it.
Like if you think about, all these techniques, and you think about, okay, what do we care about? We care about being able to collect data as fast as possible. We also care about this data that we collect. Once we use it for training, how well does it help us train a very good robot policy? And so the issue, right, with these egocentric or maybe even like the Yumi technique is that it's not exactly the robot, right? So there's this embodiment gap. And because there's this embodiment gap, you don't get the same quality as if you were to just like teleoperate it to the robot, right? So for example, I mentioned, yeah, what's the question?
Question about fine-tuning these
Yeah.
models.
Yeah.
Is it usually based off of like, the deltas of the toolhead position as well as the camera views from where you're mounting the cameras, or is it purely just camera?
You're saying what is the input to the policy? Yeah. You generally give it images, as you said, and the proprioception. So you can give the end effector pose, the current end effector pose, or generally what people do is give the 6 motor. Yeah. And then sometimes people try to give like a history of joint positions. Ideally, you should give a history of images so it has context and what it did, but then it just becomes like very hard, like intractable, because the images are highly correlated and it just takes a lot longer to train, and it just becomes much harder. So generally right now people just only give one time step of images. So like if you have 3 views, you give 3 images plus a proprioception. Does that answer your question? Okay. Why did you have that question?
Because I was wondering, like, I don't know, I was just kind of curious because, like, you mentioned when you were collecting data.
Yeah.
Right. I feel like maybe there could be potentially ways such that like you're using gloves and also handing down, like, I guess, delta positions, kind of sense, maybe like end effector positions almost.
You're using gloves to teleoperate, or you're saying?
Gloves to teleoperate.
Okay, and then?
Maybe you somehow track the position of gloves and end up figuring out the end effector distances and like deltas.
Okay.
That was just
Use that. I'm not following.
like, because you mentioned, like, from my understanding, right?
Yeah.
You're personally fine-tuning to full close. You're taking the starting position sometime later, as well as the images at the beginning, as well as the end.
Okay.
There's like you're feeding, like, I guess when you're fine-tuning the model, you're feeding it like, what exactly, like, is the delta of the travel of the end effectors, right?
That's what it tries to predict.
Oh, that's what it tries to predict.
Yeah.
So when you're like feeding it data, let's say to fine-tune, you're feeding.
Like the policy, what it sees is just, okay, there's an image, and there's, okay, what are my current joint measurements? But that stuff is not really that useful. But what the policy predicts is an action or an action chunk. And the action chunk can either be sort of like joint measurements, or it could be an end effector pose. So it'd be like, okay, given this image, where should my gripper be at? Right, so that's what your policy outputs. And so yeah, the action could be, like the current action could be as part of the input, but I think generally it's usually proprioception. Yeah.
I'm just wondering why, like, when you look at gloves especially,
Mm-hmm.
they're only really taking image data. That's why, right? As well as I guess like fingers. They're not exactly like end to end.
What do you mean by gloves taking image data?
Like when you were showing the slides previous,
Mhm.
where there were gloves,
Yeah, this one?
such as the Dex cap, for example, I was wondering like,
Yeah.
is it really only taking image as well as your finger joint positions and not really like where your wrist is in space? That's what I was
Yeah, actually, so these, actually there's SLAM with these cameras and the iPhone, right? So you, sort of this can give you the POV of the grippers, but it can also calculate, yeah, where your wrist is in space. Yeah, so, so this, yeah, essentially you have, let's say like it's a 7-DOF arm, right? So this, from here up, like this gives you IK, or this will give you the pose in space, and then you track your fingers to know sort of like, okay, what is the hand or the gripper supposed to do? Yeah.
That answers.
Okay. So yeah, I was this diagram of you know, sort of the different trade-offs, right? It's very easy to collect data with just your hands because there's no embodiment gap. You can just fold the t-shirt very, very fast. But there's this gap in terms of if you're trying to do imitation learning on this data, there's a lot of gaps. And the sort of gaps that we're talking about here, so I list some of them here. There's the kinematic or embodiment gap, right? So like, as I said, your hand, maybe you have 5 fingers, but your robot hand has 3 fingers. Maybe you're only working with parallel grippers, in which case there's only 2 fingers, but you have 5 fingers. So there's some things that you do that might not be feasible for the robot arm to do, right? If you're folding a t-shirt with like 5 fingers and you're trying to tell your robot arm to do it with only parallel grippers, it might have a hard time doing it. And then visually, there's this gap, right? So if you imagine like we're collecting data, we're going to cover DexUmi. In this setup, right? They have you sort of wear like this exoskeleton, and then there's a camera on there, but the camera sort of sees your hand or like parts of your hand. So whereas at inference time, when you actually run it on the robot, it will look slightly different, right? Because your teleop tool versus what the robot arm is doing, it's slightly different. And it's exacerbated with if you're just purely collecting egocentric data, right? Because like, imagine I slap on a camera like this, and I'm collecting data, and then you train a policy, and then you run it on the robot, right? Now it's like from the perspective of the robot, and then it just sees a robot arm. It's never seen that in the training data set. It's only seen a human's like hands, right? So that's a visual gap, and there's ways around this. And we'll see in DexUmi, they just like they mask it and then generate it. And then there's also the dynamics gap. So here I'll explain quickly what dynamics versus kinematics means, right? So kinematics would just be the equations of motion, right? So if I'm here, and then a second later I'm here, right? And there's some equation describing how I move, right, over time. That's kinematics. It's not looking at forces, right? But dynamics would be looking at, okay, I'm here and I'm here. How did I get here from here with respect to some control input? So in this case, I exerted force on my legs to move forward to get here, right? So that's dynamics. And so if you think about like when we're controlling a robot arm, okay, maybe we know that the robot arm was here and then it got to here. But how do we control it to move there? There was you control the motors by sending some current to it, right? Using torque, right? So if you think about like the force that we apply as a human to each of our muscles to do something versus the force that you apply to control a motor, these are very, very different things. And so there's this dynamics gap. Now in practice, I realized this today as I was thinking about this. If you look at like locomotion, right? Locomotion, which is like, let's say teaching a humanoid how to walk. Those kind of problems, people are very interested in learning the dynamics. But when you do manipulation, if you think about like when I do training my models, we really don't look at dynamics because we have inverse kinematics solved, and we just purely predict where the end effector should be, right? And then we sort of let the IK solver figure out what should be the motor positions and like what forces you should be sending. Whereas in locomotion, when you're walking and like teaching it, you really need to care about what is the torque that you need to send to each of these motors. So the dynamics gap is not really as much of an issue for manipulation, but it is for if you're looking at locomotion, like teaching a humanoid how to walk or a robot dog, things like that. Any questions on this so far? Okay, then we'll quickly cover DexUmi. And so I thought this paper, if you look at like where it fits on the diagram, I think it's quite somewhere in between, right? It's no longer a teleop setup, and it builds on top of Yumi because now instead of working with parallel grippers, you're working with hands, so you get extra dexterity. But there's still going to be some data quality issues because of this cross-embodiment gap. So we can quickly look at how they were able to address this issue. So this is the setup. They've learned that instead of using a GoPro, you can use an iPhone, and then they have sort of two versions for two different kinds of hands, the Inspire hand and the X hand, but fundamentally it's very, very similar. And the way they did this, to make it as close as possible to these hands, is they made sure that sort of like the lengths of each of these links are maps 1-to-1 to really close down this cross-embodiment gap. I think one thing they did is like the thumb position, they had to move it out, move it out somehow so they could wear it. But yeah, fundamentally, it's just builds on top of Yumi, and it uses the iPhone camera. But now that we sort of have an exoskeleton as opposed to the Yumi-style grippers, your own hand can be part of the frame. And so this is sort of the very simple processing pipeline where you have your image and you need to mask out you have an exoskeleton mask and you mask it and then you inpaint it with what the robot arm in theory should be seeing, right? So this is how they close the visual gap. So that at inference time, when you run into the robot, when you train your policy now sees this as opposed to this. And so then at inference time, it's sort of like, it should see something very, very similar to this. And then it should just be like, okay, I know how to react based on this image, and it should work out of the box. Any questions on this? Okay. And here's sort of like their results. I think what is interesting is, I guess these are, in practice, if you work in robot learning, these are like implementation details that are kind of important. Mostly like the action representation here, working in relative action representation. You can see if you work in absolute versus relative, you get a 90% gain, even though everything else is constant. And that's just because when you work in relative, you sort of like shrink down the space of possible things you have to predict. So if you pick and place from here to here versus from here to here, if you use relative representation, they look the same. Whereas in absolute, they will look very different, right? So by making it relative, you sort of like reduce the amount of things, or you reduce the complexity of the problem. And tactile is also cool. How much does tactile help? Let's see. Tactile helps. Tactile helps. I guess tactile doesn't help that much. But for the XN it does, for the salt task. And then inpainting helps a lot. Without inpainting, you sort of get really big degradation for some of these tasks. Yeah, so these are just some of the eval results. And this was in the appendix, sort of like, okay, Actually, maybe I should show a video of like what DexUmi looks like. Oh, that's DexCap.
We present DexUmi, a data collection and policy learning framework that uses a human hand as a natural interface to transfer dexterous manipulation skill to Brian's robot hand. We demonstrate our system's capability and effectiveness on both under-actuated.
So this is the data. So they collected data like this. What I was disappointed with was like they could have collected this data, I think, faster. But maybe if you do it faster, the policy doesn't work.
Adoption takes the form of a data processing pipeline embodiment gap.
And they talk about the embodiment gap. So this is like what I talked about, where they made sure it's the same lengths, but they had to move the wrist out. And they have the GoPro here to get a wide angle camera shot, and they have encoders throughout the arm or throughout the hand to measure sort of like the measurements. And then this is where they do the masking. Yeah, so that's basically it. And let's go back to our slides. So to achieve that task, for example, of like picking up, turning the heat on and picking up the pan, you know, how much data was actually needed, right? Because that was the topic of today's video, or today's presentation. And you see that they need 175, 310, 400 trajectories. So if you're doing this yourself, it's quite a bit. Ideally, like 5 or 10. But at the scale of like big companies or like companies working on robot learning, this is really not that much. And in terms of how they train it, I think it's just a simple diffusion policy. But they use a Dino V2 encoder. So Dino is really good at capturing. Dino is trained in a self-supervised way, and it learns. I guess like it captures good representations of what the use of features of the image, and it's good for different downstream tasks like object detection, or in this case, for training a diffusion policy. Yeah, so I think this is just interesting to see. It's just like how much data was needed to do what they were doing. But these are sort of like the general orders of magnitude. If you're just working, I guess you could, if you're training robot foundation models, the scale is much bigger than this. In this particular setup, they're not really working with robot foundation models. They're just, this is sort of like, you can think of this as like fine-tuning data. And it's actually more than what I would hope. Actually, maybe not. Considering they're working with hands, hands are higher degrees of freedom, much higher degrees of freedom. So I guess you need more data to make it work properly. And that's basically it for DexUmi. I think Kesu is going to have a quick presentation on the NYU, also related to the data collection topic. Is there any questions on DexUmi? Okay, yeah, go for it. I got you.
Perfect. So I'll just basically there are different paradigms to collect data, right? And so I'm gonna continue talking deeper into some other ways. And this is something that I basically have been working with for the past few months, working with the NYU Robotics Lab. Essentially, we built this training pipeline where we would collect data using the gripper I showed you guys, which is unassembled at the moment. But we would take that, put an iPhone on it, and then we would go and collect data. It's usually spring actuated, so you would basically press it and the gripper would close. And then the way this works is you basically take the iPhone pose to understand where in space you are, and that's how you collect your trajectory data. So you actually just need a normal human hand to go collect this data and the iPhone's collecting frames anyways. So you get a bunch of videos in, you get your pose, so you have a full trajectory data information, and then you train a policy on that, and you deploy it, and it works 90% of the time. This is sort of the inner workings of the app, where essentially that's how you record record a demo.
You built this, right?
I built on top of it, yeah. And like to go a step further, we basically also figured out a way to do evaluations without needing a robot. So imagine you have a robot that's completely, wait, can you pass me a phone? If you have a robot that's like completely, if you have already trained a model, then using this app, we figured out a way that you could technically visualize how your robot's performing. So for example, if, I don't know if everyone can see, but like, let's say I have like a robot policy loaded up right about here.
That runs on your phone, or
Yeah, that runs on my phone.
that's insane. But then how does it control the robot?
Yeah, so it doesn't control a robot, but this is what it does. It uses the same paradigm of how we collect data to also tell you where in the world should your robot move. So let's say I give it a goal point of that board, then it can sort of like help you visualize where to move or how the robot's expected to move. And especially when you get closer to the object, it's going to try to like give you some sort of an information as to whether you should close the gripper or not. And it's like an interesting way of just like wipe checking your models. So like even without a robot, you can still tell whether your robot's trying to go to the right place or
The
not.
policy is point conditioned, or
The policy is conditioned on when you close the gripper, like when collecting data. So it's still end effector pose.
like if you have a really bad policy and what you did there, would it just
Yeah.
like show something else, like another?
Yeah, exactly. Like if it was a bad policy, then it would not give us the same kind of directions it did. But yeah, so we figured out a way to basically run a policy without a robot and figure out whether the policy is working occasionally or not. So that's sort of like what we did with like just an iPhone. And yeah, that's that. Here's another setup that we had at the lab for teleoperation. This one uses VR controllers. As you can see, like there are a lot of problems with this method in terms of like you have to really tune the latency or like fix problems with latency. But despite that, like you can get pretty decent results out of that. So that's how like this mobile manipulator works back in the lab. And what I wanted to specifically talk about is what can you do. There's a new paradigm of simulations that are now being used where basically you can have your entire robot, like let's say this is my robot right here, and then in simulation I could have a playback of how exactly my robot works in real life to what happens inside of simulation. So that allows you to sort of have like a one-to-one mapping between your robot and your simulation. So now you can go ahead and collect data inside of simulation. So you don't even need like a full real-world setup in like real life. You can create an entire whole environment. Let's say I had like 5 or 10 different objects inside simulation, then I could basically have my robots like real-world movements get mimicked inside of simulation, and it could go and pick up, let's say, like the fruit kept on the table. And that's one way you could basically like augment your data or collect data in simulations. Which is moving on to this newer work, which basically, let's say you have your VR teleoperation set up right now. What you could do is you could do some sort of a simulation replay in, this is a simulation environment that has been set up. So you could take the real world data, play it back in simulation, and then you could basically generate like multiple trajectories in simulation. But the advantage of this method then becomes that because you had collected data in real life first, your simulation also starts becoming more realistic. Because the movement and the behavior clones that of real life, and that's why whatever the generated trajectories are, they are also closer to what would have happened in real life. And then you can take the same data out of simulation, and then you can basically do something called a sim-to-real transfer, which is train a model and then try to deploy the robot performing this action. You can also generate more trajectories and data with, or make your policy more robust with reinforcement learning. But that's sort of the idea inside of simulation, where you basically have a lot of privileged information of exactly what's in the environment, how things move, what the 3D coordinates are, and so on and so forth.
Can you explain? This is very interesting. Like, how do you generate more trajectories in simulation?
Uh,
Moving the objects around? Like how do you?
Yeah, so there's something called, like, there's a concept of domain randomization, which is, let's say let's say your gripper has certain limits to it. And one way of doing domain randomization could be you basically further constrain the amount of like movements that the gripper can have and see if the model policy tries to perform. Another way is you could increase the friction in the joints. Another way is you could have multiple different objects placed around in different positions, and you could use the same object, same model that you've trained, and use it inside of simulation in different positions, and then collect trajectory data from there. Or you could also something called you can also like have privileged information inside of simulation and create multiple different trajectories out of that. So for example, I can literally, if the worst way is like I can script it and be like, okay, move X 10 meters away, or like I can find out the position of my 3D object in the simulation. Let's say that's at position 10, 5, 3, and my robot end effector is in position 1, 4, 5. Then basically that's like an algorithm to get to the object, right? So in that way, I could basically randomize the number of trajectories that I can generate. So there are different ways of doing trajectory generation. One could be also based on like, you're basically doing an optimization problem with multiple different constraints. Like you can set these constraints and then you can randomize across these constraints and you can generate multiple different trajectories, which otherwise in real life, you would have had to like perform the action every single time. So you can basically scale up your data generation by like 10x, 100x, millionx. Yeah.
In this case, the trajectories are generated procedurally, and the only purpose of the teleoperation in the real world is to find out how much gap you have between the real and sim.
Not exactly true. So one way is you're trying to mimic the movements and the behaviors of the real world, right? Yeah. Now the thing is, like, let's say, is this trying to open a bottle? I can't say. I think it is. So another problem with simulation is you can't exactly see the exact, like it's very hard to set up an entire bottle opening scene inside of simulation because you need the meshes and the objects to basically react in a certain way. And because it's that hard, you could basically replay that with the mesh to give you a proxy of whether the movement would work or not because it works in real life. So rather than having to check for whether the bottle cap opened up like inside of simulation, you can still have like this trajectory replayed, and then you know the final goal is like the robot should end up in like this position, like in this goal X with a certain set of actions replayed. Then you can basically use that same amount of information in the new trajectories you generate. Does that make sense? So that's basically allowing us to be a little bit more lenient in simulation, but getting the same effect of what would have happened if you were collecting data in real life. So that's pretty much it in terms of what you can do for data collection in simulation, in real life, and in simulation. Too many words. Yeah, and so the concepts are, you want to do some sort of real to sim transfer, and then you want to like work in simulation, get a really good proxy for the model, generate a bunch of data in the scale of like millions of hours of data compared to a few hours in real life, and then you want to train that policy and then transfer it over in real life. So you can do a lot of these things inside of simulation without having to worry about the best sort of setup inside of simulation. So that's sort of the idea with like real to sim to real.
Yeah, can you go to the next slide?
Yeah. So I guess like the open questions in general are, what are limitations? There's like tactile data that's basically missing, which is touch. Steven?
I just kind of wrote these bullet points, but this is where we sort of like become more interactive and think about, what do we, what are the limitations of current data collections? If we want to train more capable robot foundation models or any sort of like general purpose models for robots, how do we get there, right? Because under the current paradigm, we talked about teleoperation. It's like very slow. There's latency. There's cross embodiment gaps. There's all these different issues. So Krish talked about real to sim and sim to real as one of the different ways to solve this. There's also like what Shiza was looking at, like you can use generative models, right? They're starting to get better, but you can imagine like maybe if you can have these video generation models and have them generate like good trajectories, and if they can also generate like the state of the robot arm, and if you somehow use that to train your policy, it would be amazing, right? But I think there's still a long ways to go for that. We know that teleoperation works, but it's sort of like hard to scale, and maybe you want to make it. There's different problems there. Like you need more dexterity. You need active perception is like if you think about your when you're doing things, you also use your head and you look around. But a lot of these setups are stationary, so it's just like a fixed camera. So active perception is another field of research, and then kinesthetic teaching could make a comeback. So there's actually like Aloha Lightning, which is like in review right now, and what they do is like a variation of kinesthetic teaching where instead of the Aloha setup, they'll take the Aloha grippers and the human will be much closer to the grippers, and then it will sort of like control it much closer next to the grippers. And then, can we get away with scaling up? I'm not sure what I meant here, but egocentric data is much easier to scale, but there's this gap. So how do we solve these problems? So these are sort of like the problems we're thinking about. Does anyone have any sort of questions or like things they want to say? I think this is like the time to talk about this and think about this together. What do you think are some lessons from the self-driving car world that we can apply to robot learning when it comes to data collection?
We put a humanoid in the car seat, and then we'll train it that way.
You put a humanoid in the car seat, and because self-driving is already solved.
Yeah, you record the guy. You record the guy looking. You record the guy driving.
You record the guy driving.
That's $1 million. Yeah, that's great.
I mean, I always said, like. You don't need to solve the self-driving car problem. Just solve the humanoid problem, and the humanoid can drive the car.
Yeah.
And then
if you solve the humanoid, everything gets solved.
Yeah.
That's why it's worth it, truly.
What do you think, Shiza?
About the self-driving thing or
generally, because you've been thinking a lot about data collection too, right?
For the kinesthetic teaching, not as much related to data collection, but there's a really cool paper that was kind of like RLHF, but in the physical world. So I think the paper is called Dagger. And they basically, whenever the robot does something that is not according to policy or out of policy, out of distribution, whatever, somebody just presses a button on the robot to override the data collection that's going to happen, and then like moves the actual physical. You mean like the rollout of the policy, and then? Yeah, as in like let's say I'm folding a T-shirt and something goes wrong. The robot like messes up or like starts being static. You press a button. You press a button to like override it, and you just move the robot arm to the right direction or the right place, and then press unpause and add to the data like that to override it. I guess that's the only thing for kinesthetic teaching that I think could be applicable. Other than that, I probably don't think we would want to use this for data collection, considering it would take so much time. I think for scaling data collection, other than the cross-embodiment gap, something that I've been currently thinking about is with LLMs, it seems like scale of data has helped us to get to better reasoning. Can we do that with just getting a lot more data instead of more reasoning policies or architectures? And can data just solve that problem? I think with tactile, especially can, because you have force feedback to determine how much the arm should grasp. But I don't know if that's going to be enough to like solve a bunch of the robustness problems. So wait, you were saying like, I wasn't sure what you meant by the reasoning stuff. So like robustness and a lot of the, I mean, we talked a bit about this, but the vertical part of making it more reliable and robust, how can you solve that? You can solve that with more reasoning like architectures perhaps, or can you just get more data that
I think like
tactile to solve that?
Like if you do Dagger, I think that essentially solves it. Dagger is essentially, I think, a more elegant way than doing it offline, because essentially you're doing it online. You're running your policy, and then you're like, okay, this is bad.
I'll show you how to fix yourself, and then do this like online, as opposed to what people would do is, oh, I noticed this is bad. Okay, I'm gonna offline collect some more teleoperation data for this edge case, and then add it to the data set myself. But your way of doing it is like much faster of iterating, and perhaps like people who are deploying, they're doing some version of Dagger right now, I think. Yeah.
So like another way that Dagger, or like the opposite of Dagger would be, you basically when you're training your model, you label the failed case.
Right.
So then you end up training with the failed case, and so based on the language conditioning, the model learns about whether it should do it or not.
Okay, any final points? Okay, cool. Well, thank you for coming this week. For next week, we have not decided the topic because we're supposed to do a choral recap, but we're going to do that in 2 weeks, I think.
Yeah.
And
Midterms.
next week is the midterms. I don't have midterms though, so. And
Yeah, I'll present the one next week.
it's just an hour, right? Like, come on, you can squeeze out an hour for your midterms. Okay. All right. Thank you guys for coming, and thank you. Yeah. Thank you.